Hi everyone. We are going to do another tutorial about using AI for design tasks in Rhino. So for this exercise, I prepared a file like this to test if we can actually use AI to help us design like a structure with this sort of aggregation. And I have basically these volumes that I want to be placed inside of this tower structure. So I'm going to ask AI for suggestions and see if we can basically work with it to find placements for this. So I'm going to basically develop some tools, some workflows, and share with you like how you can approach this task. So let's go to Microsoft Copilot. So first thing I'm going to do is how do we put this information to AI, right? So we have to think about it. First things first, AI doesn't take in geometry information like we would like it to be. So what we can do is basically write a script that exports this geometry data in a text file or copy the coordinates of these points so that it can know the type of structure we're working with, and then give it some dimensions for these volumes. So let's see if this works. So I'm going to measure, I have like a 32 by 32, and this is, let's see, 96. Let's scale this up to 48. Okay, so that's the volume that I want to work with. So this is 24 by 24 by 18, but we're going to keep it as 24 by 24. Let's scale it up as well. So this should be 24. All right, so these are, let's measure the height for this. So this is 16. It should be 16 as well. We're going to have 4 of these. And this should be, I think 12. Okay, so we're going to have 8 of these. All right, perfect. So that's kind of the setup that we have. And in this model, each volume is 6 inches. So we have to specify the coordinates of these, right? So there are a bunch of ways we can do it. One of them is you can use Grasshopper basically to get the coordinates of these points or get the centroids of these points. So let me start Grasshopper. The other way is to ask Microsoft Copilot. So let's prompt it basically. So let's say I want you to help me design a towering structure. I have a collection of voxels. Help me write a code, let's say Python code, to output the center coordinates of points so that you have the geometry data. All right, so let's see what Copilot does. So I'm going to move this halfway here and then move it up here. This is my Grasshopper. You can also do like create a geometry container, right click, set multiple points, select all of these. I actually have some lines, so let me first delete the lines. So I go back here, set multiple geometry, so I'm going to select all of the boxes. If you do volume, the volume should give you the centroids. So these are my coordinates essentially, and if I do a panel, these are the XYZ coordinates of the points. So if you right click, do copy all content or copy data, you should be able to paste it here as coordinates basically. But let's see. So it said, let's start extracting center coordinates from your voxel collection. So it also gave me a Python snippet that we can basically run in Rhino Grasshopper. Let's see, this is, so voxel size is actually 6. Let's write that up. My voxel size is 6 units, is 6. So it's giving like a voxel list. So I want to say I'm going to select geometries in Rhino. I want to plot their centroids. Give me the code in edit Python script. I also have it here. We can just copy paste it, but just wanted to show you how you can actually use AI to do this. So it says plot centroids. So we can just copy this code, go back here, edit Python script, and then if I paste it here, run it, it says select geometry to define centroids. And then let's see. Okay, so it didn't print, but let me figure out if, oh, it just put points, I guess. Let's just select point. Well, these are all the points of the boxes. Well, let's delete this and then say this gives me points. I want to export a list of point coordinates so that you can process it. Okay, it's going to tweak that script. So let's go back here. Here's a version, and it's going to basically find the centroid, and it's going to print the point. All right, so then it's going to export. So let's paste this up, run this. It's probably going to print it as XYZ. All right, so it plotted all of them here. Let's go back to the Python code. Where's the Python code? Okay, edit Python script. So 812 points. All right, there it is. So these are all the point data. So what we could do is you can just copy all of this. For some reason though, this is like not accurate. So it's a bit, let's say it has all these like small increments. So I'm just wondering if it should flatten it to integers, or like maybe these are slightly off. So I might have shifted this model a bit. Like, well, let's check Grasshopper. If Grasshopper gave me actually better result. So what I can do is just copy all of this content, create a notepad file, and just like paste it here. So these are all the points, and save as, let's say, points. All right, and then now what we can do is actually put those points inside. Let's find those points. Let's see. All right. So these are all the points in the model. Help me find suitable empty sites or voids that can accommodate the following volumes. So I want one 24 by 24 by 24, 4 16 by 16 by 16, 8 12 by 12 by 12. Boxes placed. write a Python script that can place these volumes and differentiate their colors. Shade colors of each group. All right, let's see what it can do. Then I can also use Grasshopper to filter this data, but let's see. So it says convert the list of center points to 3D, use spatial resolution based on voxel size, identify occupied regions, insert boxes into available voids. Okay, so it's giving me some code now. So red, green, blue, box fits, mark box, count size. Visualize the inserted boxes in Rhino. Each group will be color-coded. Export the coordinates or bounding boxes. Can you parse? Can you process the point data and give me a Python code that will place the volumes at the best sites? So it's processed the voxel centers and built a spatial occupancy map. Now let's write a Python script that intelligently places requested volumes. So scan for empty regions that can fit 1 box, 4 boxes, 8 boxes, and convert it to dimensions because my unit size is 6. So let's do select points, delete these. All right, I could have always used this as well. Smart placement box, and insert in the largest possible voids, color-coded volumes, modular logic. All right, so it gave me some Python code. Let's try it now. Edit Python script again. So I'll just create a new script. Paste it here. Let's run it. Select voxel center points. Oh, I just deleted the center points, so let's pull them back in. Okay. And I select all the center points. All right, so it placed basically the potential sites. So if you go to shaded view, you can see it basically found these sites for the volume. So it basically fit the 8 blue volumes here. Interestingly, it found the site. This one is not too accurate. These as well. So it's kind of large. I'm also missing the red one. Let's see if it kind of calculated it or missed it. Select color. So I'm going to hide these. Go back to Grasshopper and disable this preview as well. Okay, so I'm seeing 2, 4, 6, 8 blue boxes and 4 green boxes. So let's write this back. I'm seeing 8 blue, 4 green boxes. I'm not getting the big 24 by 24 by 24 volume. So it's spans 4 by 4 by 4. So it probably didn't find a suitable site for it. Your voxel field likely has enough space overall, but not 4 by 4 by block empty voxels. So it can basically change this sorting or looking strategy. So sort box specs from largest to smallest, scan entire grid, only proceed to smaller boxes. Okay, replace this part of the script with this, it says. So let's try that. So let's go back here for count. Where is this? Box specs. Okay. So we should just replace with this. Let's see. So I'm going to delete these, show, run it again. Okay, now I see the green ones again, but not the red one. So it's finding the same sites. adaptively with mutation or stacking logic. Would you like a diagnostic script to highlight all voids? I'm looking for possible sites with less intersection with the existing volume. It's okay to intersect a bit. I can modify it later. Give me the placement from largest to smallest. So it's shift strict ecology to low intersection tolerance, prioritize larger volumes first, allow partial overlap. Okay, perfect. Because what I want to do is actually get those sites and then filter those boxes at those sites. So we can do that in Grasshopper as well. Okay, so it says smart placement. Let's see if it does it. So I'm going to go back here, copy paste it, voxel center points. All right, so now I got a red site as well, which is actually not bad at all. So it's giving me these sites. So let's see. It found these areas. So this is kind of overlapping, but it's fine. Like we can also shift it if we want to. But it's kind of a starting point. So now if we want to, let's say, filter these out, this is what you can do. You can go to Grasshopper and you can put like a geometry container. So what I want to find is I want to first select these boxes, hide them. This is not accurate though, like it's intersecting existing geometry, so we should probably like ask it to modify that. I see some of the blue and green boxes overlapping. Sure, these spaces do not overlap. Okay, so dedicated placement. It's going to update it. Let's move this here. So let's see, revised. Here's updated core logic. Can you give me the updated full script? Okay, it prioritizes larger volumes, allows partial intersection with the original voxel field, prevents any overlap between place boxes. Let's see if it does it. So that's interesting. So I'm basically giving it a design prompt, right? So I'm asking for potential sites. So rather than me going in and trying to find these places, I can basically get some help on this task. All right, so it's asking for, okay, it's still overlapping though. Green and blue are still overlapping. Overlap a bit. They do not with each other. If like this problem persists, like I'm just going to modify it slightly and show you the next step. Okay, no intersection allowed between placed volumes. So was it allowed in the beginning? Prevents any overlap between placed boxes. Well, all right, so let's see. Let's run this. Well, it's still giving me the same issue, but it's okay. I mean, I'll just show you the next step. So let's say this is placed here. And This guy, let's move it down a bit. I have another blue one here, I think. Let's pull it down all the way here. Okay, so it can be anywhere I want, essentially. But what I want to do is find some sites for these boxes. So let's move it here. And let's move it here. So let's see. I'm going to do select color. Select color. Okay, so maybe this one, we move it out here. Okay, so let's say these are my spaces. Now what I want to do is be able to filter the boxes in there. So I'm just going to right click, select multiple geometries, and I'm going to hide these. And then I'm going to, this is the existing volume of boxes. So what I want to do is I want to check if any of these boxes are inside these volumes or not. So one way we can check it is you go to get the volume, and there should be, let's see, if it can check for intersection as well. We can check for intersection, intersect shape. Let's see, point. Maybe we go to vector. There was okay, point in curve command. Point in volume, maybe. Test the numeric value to see if it's in the included domain. All right, maybe we can ask it to write a Python snippet. Okay, write me a Python snippet that can, if a list of point coordinates are inside a list of given volumes, I want the output to be a Boolean list. Check each point against all the volumes. Okay, write me a Python code that can check it. If a list of point coordinates, let's call it A, list A, so given volumes, list B. I want the output to be a Boolean list of true or false. Check each point coordinate, list A, against the volumes, list B. Let's see, I was a bit more specific for this prompt. I want to implement in Python Grasshopper. Okay, so it's very straightforward. So let's see, Python script. So list A and list B. So I'll just name this as list A. And this is list B. So list A is a bunch of point coordinates. List B is a bunch of geometry. So I can go here, right click, list access. And the output is flags. So let's see. I can rename this output as flags. So gave it an error. Okay. Let's ask it to fix it. List of Rhino box objects. So maybe we can do type ins box. Well, that still doesn't like it. It's giving now a pre-processing Okay, I guess it fixed that. Okay, now I got a Boolean list basically of true and false. So if I look at here, some values could be true. Let's see, they're all false though. I'm getting only false. Some of the boxes intersect. Well, maybe the centroids are out of them, but the boxes in there could be. Can you modify the list A with boxes? Another list of boxes. Okay, so it's going to look for intersection now. Okay, perfect. So let's do it this way. And it needs to be a box as well. So I'll just place this in here. I'm not seeing any true. Okay, why is that so? Well, region intersection, solid intersection. Yeah, I think we did it correct. So these are the boxes. These are the volumes. It's giving flag false. Maybe it's not even entering here. I'm just curious if it even goes here, so I can type in like a print. Yeah, it's not even entering inside the instance. So what if we just do we don't check for this, or should this be defined as a box? Type ins as box. I mean, both of them are boxes now. But I don't see. I am passing in geometry lists. Help me check for intersections. Okay, it's also going to look for brep, so maybe this would work better. All right, so let's run it. Now it's giving an error. Here's the corrected version. Another error. Oh, okay, so let's go back. Okay, this bounding box intersects method doesn't exist. Can you implement it in another way? Okay, it's going to do for manual overlap 3 dimensions. I think this should be fine. Let's see. It's still getting bounding box. Do not use bounding boxes. Look for geometric overlaps. Okay, this is not getting me anywhere, so maybe we do something else. So how can we check it? So I was looking for volume inside, and that's giving me false basically from a list of points. But it's kind of weird as well because, like, for instance, this point's volume would be inside, like center point will be inside this volume, right? So it should give me a true. And what I wanted to do was kind of filter these voids and bake another geometry so that these will be placed inside. Maybe we should go back to the point version and see if the bref contains them. Let me see if there's something else. So there's like analysis. There's point in bref actually. Maybe we can use that. So okay, so bref for inclusion test, point for inclusion test. So if I put this in and put this in, the data failed from point to bref. So this is reference bref. Okay, so this is bref, this is point. So this should give me list. But what we want to do is check for all of these, right? So I need to graft this data. So that will give me 812 points of filtered data. And some of them, let's see if some of them are true. I see one once in a while. I think there are some trues in there. Okay, so then we can do, what can we do? So this should basically 812 values. If I do flip matrix, now this is the point data. So if any of these lists, so this is for like, let's say 148 volume or voxel, if any of these is true, because I'm checking for 13 against 13 volumes, if any of these is true, that means like that volume intersects with one of the volumes. So we need to remove that essentially. So I can simply write like, give me a simple Python code that looks at a list of Boolean values, and if it contains any true value, it outputs false, else it outputs true. So what this will do is help me filter out the points essentially. So okay, so the invert Boolean list, example usage result. Okay, so return not any Boolean list. So it's basically this. So what shall we do? So this should be, result is this. Let's copy it. We can delete this. Input should be flags. It's a list of Booleans basically. So we do list access, type in Boolean. So this goes here, and the result should be 1. So there's true and there's one false, right? Perfect. Now what we can do is we could do call pattern. So go back to this list of geometry, and this data now needs to be flattened so it becomes a single list. And if you look at here, I'm going to hide it. This called list should actually have the cleaned out voxels, right? So we started with 812 voxels. Now I ended up with 728. So that means like it removed 100 voxels that intersect with these volumes, essentially. So we can also do dispatch with the same logic. So if I feed this in, look at the geometry output. These are the good voxels, and these are the deleted voxels. So you can see it deleted these where the other volumes existed actually, right? So these guys intersect with these volumes. So it found out the placement for those, and we can basically delete these, or you can simply bake this into a new layer. So you can go back here, clean voxel, and you can simply right click, bake, clean voxel, and that should give me essentially the voxels that do not have any intersection with these volumes. And you can see it's actually pretty accurate. So it kind of removed all these voids, right? So I can move these things around with this code and kind of filter out the structure on the go and bake whatever configuration I want to make. So my Copilot didn't actually like implement it the way I wanted to, but still like we were able to use some native Grasshopper components. Like under surface tools, there's point and brep, and you can check it against like volumes against other volumes. So that can help. Otherwise, like if you want any other type of tools you want to be implemented, you have to give this type of geometry data to Microsoft Copilot, so it kind of parses it and gives you kind of sites. Maybe that requires a bit of back and forth, but give it a shot and see how it goes. Okay.